Hello, and welcome back to a video series on MAC 1140 Precalculus Algebra. My name is Sean Perry. These are guided notes number 26 in the series on section 5.4, Hyperbolas. Let's begin with the locus definition for a hyperbola. A hyperbola is the set of points whose distances to two fixed points has a constant absolute difference. Essentially, we're given these 2 points, which will be our foci, or focuses, for this figure. Every point xy on a hyperbola has a distance to each focus, and the difference between these is some fixed constant called d. Saying that we're looking at the absolute difference just means that it doesn't matter if instead we took d2 minus d1 for this other branch over here to get our d. For this branch over here, f1 is closer, and so d1 will be smaller, and d2 minus d1 will give us the positive quantity. While on the other hand over here, f2 is closer, and so it's d1 minus d2 we should take if we wanted to get this fixed positive quantity d. In this sense, the absolute value of the differences is really the thing that is constant. Let's break down a little bit of the anatomy of the hyperbola. First, let's look at one with horizontal orientation and a center at the origin. When we speak of the orientation of a hyperbola, we're talking about the positioning of the vertices and the foci. They will lie along a common line, which cuts this orange hyperbola into 2 pieces. We call this axis that cuts through the hyperbola its transverse axis, and this other axis of symmetry, which does not intersect the hyperbola, we call this its conjugate axis. One feature of hyperbola are that they have asymptotic behavior. It has a cross of 2 lines, which have opposite signed slopes of one another, towards which the hyperbola converges. The slopes of these asymptotes are characterized by a ratio to the length of the distance between the vertices. The distance from the center to one of the vertices we will call A, and there is a certain other number b, which in ratio will give us the slopes of these asymptotes. We will call these positions here of distance b along the conjugate axis the co-vertices of the hyperbola. But unlike our co-vertices of the ellipse, they are not positioned on the hyperbola, but are instead off of it. C is familiar, however, because C is going to again be the distance from the center to a focus. Here is the standard form of the equation of a hyperbola, horizontally oriented and centered at the origin. Why would such an equation have this asymptotic feature? If we solve the equation for y, we find the following: plus and minus b over a times x times the square root of 1 minus b squared a squared over x squared. However, as x becomes arbitrarily large, this term goes to 0, and so the overall square root just goes to 1. And we get that for large values of x, the behavior will be something very similar to these lines. There's also another Pythagorean relationship, just like there was for the ellipse. But now C is back to playing its usual role as our hypotenuse. I won't endeavor to prove this here, but suffice it to say that if you know that this equation is going to give you asymptotic behavior as such, and you follow up from the hyperbola to this corner, which also has length c, and we take the points equidistant to this point, i.e. a circle centered at the origin, and follow that back to its intersection with the transverse axis, we will find a point. And if we were to take this point and plug it back in to our locus definition, we would find that it is indeed the focus that satisfies the locus definition for the points along this orange hyperbola. Another important fact about the distance involved in the locus definition of the hyperbola is that the difference between these distances to the focus is the length to A, which we call the length of the transverse axis. We can see why that's the case just by measuring. If I go from this focus to this vertex, that's length c and also a, so c plus a. On the other hand, from this focus back to this vertex, is c minus a. And so if we take their difference, we just get 2a. Let's look at some other forms of the hyperbola. Still with a center at the origin, we could adjust and put our transverse axis vertically and situate our foci and vertices along it. We would still call by 2a the length of the transverse axis, but now we move up vertically by a in order to get to our vertices. Note that the difference between the two equations in standard form is that now y is the leading term, which is positive compared to x. The a and b have stayed exactly where they are, and unlike the ellipse, there is no reference made to whether or not a and b are bigger or smaller than one another. Instead, we only care about making sure that a is associated with the positive term, and that positive term tells us which axis will be our transverse axis. As before, if we shift our center to hk, it doesn't really change too much, except for changing our zeros in the previous equations to h's and k's. I like to look at the equation for the asymptotes also just in point-slope form, because it lets us see that all we're really doing is applying this transformation of shifting over by h and up by k. If the transverse axis is horizontal, and we say it has horizontal orientation, then we're going to have x be our leading positive term and a associated with it. Notice that in these kinds of situations, the slope of the asymptotes has an a in the denominator because a is playing the role of an x value. And when we look at rise over run, we put the y value on top. On the other hand, if we look again at a vertically oriented hyperbola with a center at hk, now a is playing the role of a vertical quantity. And so when we talk about the slopes of these asymptotes, it is a that we find in the numerator and b in the denominator. Let's begin with the guided notes. Question number 1 asks us to identify the vertices and foci of the hyperbola associated with this equation. Notice that we can easily pick out what's a and what's b. Y, being the positive term, tells us this is a vertically oriented hyperbola. And noticing that there are no h and k values, the center is at 0, 0. If I go up and down by a, we'll get to our vertices. Find out what our foci coordinates should be, we need to find out what c is, which we do by solving this Pythagorean relationship. This tells us c is 106, and so going up or down by 106, we find our foci. Question number 2 asks us to write the equation of a hyperbola who's centered at the origin, where the length of the transverse axis is 4 and the curve passes through a certain point. If the transverse axis has length 4, then a is 2. And if this is horizontally oriented, then that term will be positive and we'll get the a. All that remains to complete the problem is to find out what b is, so we plug in all of our known values for this point 5 minus 2, and then solve for b. Or at the very least b squared, because that's all that we need for deriving the equation is the term b squared, which is 16 over 21. Here we're asked to find the standard form of a hyperbola with vertices as given, that also passes through a given special point. Because we can see that the vertices are horizontally displaced from each other, we know it has horizontal orientation. And we can also see that it's centered at 0, 0, and that a is equal to 4. Plugging in these knowns, 6 and 20, for our x and y respectively, along with a, we can solve for b. To find b squared is equal to 320, which gives us the following form for our equation. For question number 4, they give us the equation of an asymptote and also the coordinates of the vertices. If I know the coordinates of the vertices, and I know this asymptote, to find b, I need to find where they intersect. And so I'm really asking about when is my y value going to be equal to 3? Well, this will be when x is equal to 9, and that tells us our value for b. Because it is vertically oriented, we're going to put y squared over 9 first, and then minus from that x squared over 81, or 9 squared. So we put 3 squared here and 9 squared here, corresponding to our vertical and horizontal aspect ratio. For this question, we need to find a and b, which we can find first by orienting the hyperbola. We see it as horizontally oriented. To go to a vertex from the center is to go over by 3, so a will be 3. And if I want to go up from there to the asymptote, that's going to be up by 2, so b is 2. Plugging these things into our equation, we get the following. Question number 6 is similar. We see that it's centered at the origin and that it's vertically oriented. Going up by 6 units brings us to a vertex, and so a must be 6. Going right then by 3 units and up by 6, we arrive at the asymptote. This tells us that b must be 3. And so we have y squared over 36 for our leading term minus x squared over 9 equal to 1. Number 7 asks us to write the equation of a hyperbola centered at -2, -1. They give us the length of the vertical transverse axis. They say it's 8, and the length of the conjugate axis is 6. This tells us the vertical orientation of this hyperbola. It tells us that a is equal to half of 8, or 4, and that b is equal to half of 6, or 3. Now, this y value is our k. It needs to go along with the sign change right here next to the y, because this is y minus k in the formula. And then x minus h will minus 2, so we need an x plus 2 here. Now, it's vertically oriented, so we're going to put our y value first over a squared, which is 16, and this one will get our b squared and the minus sign. All set equal to 1. That's our equation. Number 8 asks us to find the center, vertices, and asymptotes of the following equation. We note from this equation that it has vertical orientation, because y is the positive term, that a is equal to 4, which is the square root of 16, and b is equal to 7, or the square root of 49. So we can read off that the center is at 2, 8 from noticing our h and k respectively. And if this is vertically oriented, we're going to add a to get to the vertices. We're going to add it to the y value to make this go up and down. So we do that, and we find the points 2, 4, and 2, 12. To write the equation of the asymptotes, we need to first take note that their slope will be plus and minus a over b. That's because here a is playing the role of a y value, and so it should go in the rise part of the slope. I think this is perfectly fine. You can even just bring the plus 8 over, but we could also solve this and put it in slope-intercept form if we wanted to. Question number 9 asks us to sketch a graph. We notice that this has a center at -1, -2. That's here. We notice also then that the slope of the asymptotes is going to have slope plus and minus 1/3 and pass through this point here. Number 10 asks us for the equation of hyperbola that fits this certain asymptote with the smallest possible whole numbers for a and b. Well, the ratio of a and b is going to be 3 to 4. Specifically, if we're in this form, it has a horizontal orientation, and a corresponds to x values and thus is on the bottom of the slope. Now, we cannot reduce 3/4, and so 3 and 4 are our smallest possible whole number values for b and a respectively. For number 11, they ask us to consider a hyperbola which has vertices at these locations and a foci at this location. They'd like the standard form of the equation. We can note here that because we're changing a y value, we have vertical orientation and a transverse axis length of 12. That's the difference between -3 and 9. If I take half that, I get my value of a, which is 6, and the midpoint between these two vertices will be my center, which is at -3, 3. We take a look at this Pythagorean relationship, and we can solve it for b squared, and plugging in our values, we find that b squared is 100. So that gives us our a, our b, our h, and our k. That's enough to write the standard form of the equation. We have h as -3, so that goes here as a +3. We have k as +3, that goes here as a -3. A was 6, that goes here as a 36, and b squared was 100, so that goes right here. Number 12 asks us to consider a hyperbola which has certain vertices and a certain foci, just like the last one. Here we can see horizontal orientation because it is the x values which are moving. The transverse axis length is 12, and so a is 6 again. The center will be the midpoint between these two values, -12, -4, And so we're going to put a plus 12 and a plus 4 next to our x and y respectively. It's horizontally oriented, so we put x squared up front, and the y term becomes our negative. We have this distance to go from our center to our focus, so that's our value of c. And plugging those values into the Pythagorean relationship, we find that b squared is 100 again. And so that gives us this overall standard form for the equation. Question 13 asks about the vertices and asymptotes of a certain general form equation, which we can put in standard form just by dividing by 144. This gets us a and b values, as well as being able to see that our center is at 0, 0. And this in turn lets us solve for c, which tells us where our foci are. And the a and b also let us know the value of the asymptotes. So the two lines which correspond to those asymptotes will relate to the ratio of b over a. Again, this is horizontally oriented, and so a values have to do with x values, and that's why it appears at the bottom of the equation here. It's rise over run after all. Question number 14 asks us to write this general form equation in standard form, which we can do by completing the square. I would first rearrange things to group x's and y's, bring my constants to the other side. Factoring out a 9 and making enough room, I can complete the square by adding 4 inside. And also factoring out a minus 36, I can complete this square by adding 4 inside. Of course, I really added 9 times 4 and minus 36 times 4, so that's what I want to add to the other side to balance. Once I square this away, I get the following. But then dividing both sides by 324, we simplify to x plus 2 squared over 36 minus y minus 2 squared over 9 is equal to 1. This is our standard form of the equation. The next two problems are pattern matching problems. We want to see, first of all, what is the orientation and what is the center of these graphs, and that's enough to distinguish them. This one has a center at 3 minus 2, and it has vertical orientation. The only one like that is the first one, where y is our positive quantity, and we are at 3 minus 2 for our center. B also has vertical orientation, but its center is at 3 positive 2. And C has horizontal orientation, making it this of the three. For 16, we're supposed to match equations to their conics graphs. Now, what we want to do is note whether or not we have a difference of sign, as in the case with B and D, between the x and y terms when we bring them over to one side and set them equal to 1. If we have a positive instead, as in A, C, and E, then we're going to have either a circle or an ellipse. We have an ellipse if the two denominators do not match. If the two denominators match or are just equal to 1, then we have a circle. So using this and the values of the centers, we can distinguish the two circles and the two hyperbolas and the ellipse and assign these values to them. For this next one, let's start with a picture. They talk about the sides of a nuclear power plant forming a hyperbola. That's because a nuclear power plant tower is a hyperboloid of revolution. That is to say, we've taken a hyperbola and rotated it 360 and swept out this three-dimensional shape. They tell us that the height is 586, that the width at the narrowest point is 158, this narrowest point is 437 feet above the ground, and at the ground level, it's got a width of 302 feet. The question is, what is the width of the tower at a height of 12 feet? First, we want to write this down according to some kind of picture. Let's put the origin right here along the transverse axis. Now, if this is 158 wide, then the transverse axis will be 158, and our value of A will be half that. That'll be the coordinate of this vertex. On the other hand, for 302, we then know that this point has coordinates 302 and minus 437 if we go down by 437 to get there. Using our value for A and a point, we can solve for B in the usual way. Some of the numbers get a little ugly in this case, but that's okay. The question is now, what is the value of this width, which we could find if we just had this value of x. The value of x when y is minus 425, or 437 back by 12. Up off the ground. And we're going to be looking for twice x to get this total distance across at that point. So plugging in what we now know in terms of a squared, b squared, and this point's y value, we could solve for x to find 148. The diameter is twice that, and so twice that is 296. This last problem asks us about two radio stations that send simultaneous radio signals to a ship that consistently arrive with a time delay of 0.0001 seconds. Now, because they're traveling at a fixed speed, that time delay always also means a fixed difference in the distance of travel for those signals. What is that difference? The difference between these two distances? Well, that's going to be the speed at which the signal is traveling times the time delay. The difference between these two paths is going to be 30 kilometers. And in order to keep that the case, we're going to have to stay on this hyperbola. So now, if I know that these are 170 kilometers apart, with these radio stations playing the role of our foci, then 85 is going to be half of that, which will be our value of c, or the distance from some middle point origin over to those radio stations. But we now have c and a, because if we remember from the intro, d, this absolute difference d between the two distances to the foci, has to be of length 2a, the length of the transverse axis. Having c and a, we can then find b, or at least b squared, and that gives us enough to write our equation. I've positioned this horizontally, and so we're going to have our x squared as our leading term. It's over a squared, which 15 squared is 225, and b squared we just derived to be 7,000. So we put minus y squared over 7,000 equal to 1, and that'll be the end of that. Okay, that's going to do it for this video. Thank you very much for your patience, and have a great day. Good luck with your studies. I'll see you in the next one.